In this video, we're going to begin section 5.4, and it's finally time for the Fundamental Theorem of Calculus. And in this section, we're going to evaluate definite integrals using this fundamental theorem, understand and use the mean value theorem of integrals, and we've had that mean value theorem for derivatives, and it has a corresponding theorem that ties into this integration. And we're going to find the average value of a function across a closed interval and understand and use the second fundamental theorem of calculus. So let the fun begin. You've now been introduced to the two major branches of calculus. First was differential calculus, and we introduced that with the tangent line problem. And recently, integral calculus, introduced with the area under a curve problem. At this point, the two problems might seem unrelated, but there is actually a very close connection between the two. This connection was discovered independently by Newton and Leibniz, and it is stated in a theorem that's appropriately called the Fundamental Theorem of Calculus, the FTC. Informally, the theorem states that differentiation and definite integration are inverses, in the same sense that division and multiplying are inverse operations. To see how Newton and Leibniz might have anticipated this relationship, consider the approximations shown below in the figure. The slope of the tangent line was defined using the quotient delta y over delta x, or the slope of the secant line. So down here, you know the slope of our secant line was delta y over delta x, or the slope of the tangent line is also delta y delta x. Similarly, the area of the region under a curve was defined using the product delta y times delta x, or the area of a rectangle. You know, here's our delta y, delta x is the width. The area of the rectangle is, we multiply those two, where for the slope it was their quotient. So, at least in the primitive approximation stages, the operations of differentiation and definite integration appear to have an inverse relationship in the same sense that division and multiplication are inverse operations. The fundamental theorem of calculus states that the limit processes used to define the derivative and the definite integral preserve this inverse relationship. And here in Theorem 4.9 is the fundamental theorem of calculus. If a function f is continuous on a closed interval from a to b, and capital F is an antiderivative of f on that interval a to b, then the definite integral from a to b of our function f of x dx is, remember the capital F is the antiderivative. The antiderivative function f, where we run the upper limit b through it, minus the same antiderivative f with our lower limit a run through it. And let's take a look at this guideline box. If there's any confusion, this should clear it up. So the guidelines for the fundamental theorem. Provided you can find an antiderivative of the function, you now have a way to evaluate a definite integral without having used that limit of a sum definition. So when applying the fundamental theorem of calculus, the following notation is convenient. So here we start out with our integral sign, the integral from a to b of our function f of x times dx. When I was learning this, I always imagined that this definite integral sign, when we do the antiderivative of the function, this definite integral sign slides across the function. As we do that, we take the antiderivative of our function f, which is capital F of x. The dx, the differential, is also consumed when we take the antiderivative, and when the integral sign gets to the other side, it becomes a bracket. And at the top of the bracket is our upper limit b, at the bottom of the bracket is our lower limit a. And then to actually evaluate it, we take that b and plug it into the function for x. So we get f of b. And then we take our lower limit a and plug that into the function for x, and we get f of a. So f of b minus f of a. And you know, here with this notation, it still might be a little confusing. Let's look at a real simple example. And let me even make this a little bigger. So they This example is a nice easy function. It's the definite integral from 1 to 3 of x to the third dx. So here's our integral, the definite integral from 1 to 3 of x to the third dx. When we take the antiderivative, and our integral sign, again, I imagine it slides across the function. When we take the antiderivative of x to the third, we get x to the fourth over 4. Remember, when we take the antiderivative, we raise the exponent by 1, x to the fourth, divide by the new exponent, 4. And then our integration sign turned into a bracket from 1 to 3, our same upper and lower limits. So to evaluate it, first we put our upper limit in for x. So 3 to the fourth divided by 4. 3 to the fourth divided by 4. And then we subtract when we run our lower limit through the same antiderivative. So 1 to the fourth over 4. Well, 3 to the fourth over 4 is 81 fourths. 1 to the fourth over 4 is 1 fourth. If we subtract, we get 80 fourths, or 20. Now you might wonder, when we took the indefinite integral, we had a plus c. We created a constant out of thin air, because the indefinite integral was a family of functions. It is not necessary to include that constant of integration c in the antiderivative, because when we take the antiderivative of f of x, we got capital F of x plus c, and then our limits were from b to a. When we plug our first upper limit in, we would get f of b plus c, and then minus, in parentheses, our grouping symbols, run the lower limit through, f of a plus c. And when we distribute this negative, we're going to have minus f of a, and then that will be a minus c, which will cancel out this plus c. Plus c and minus c will cancel out, and we're left with our fundamental theorem, f of b minus f of a. So let's try these three examples. Our first one is the definite integral from 1 to 2 of x to the x squared minus 3. So the first thing we want to do is take the antiderivative of our equation. Antiderivative of x squared will be x to the third divided by the new exponent 3 minus 3x. And when the integral sign comes over, it comes over as a bracket from 1 to 2. And now we want to run those limits through. First, we're going to plug in the 2 wherever we see an x, and get 2 to the third over 3 minus 3 times 2. That is our upper limit run through our function. And then we're going to minus our lower limit run through the same function. So we run the 1 through wherever we see an x, and we will get 1 to the third over 3 minus 3 times 1. So here we have 2 to the third, which is 8 over 3, minus 2 times 3 is 6. And then we have 1/3 here, and we distribute the negative. That'll be a negative 1/3. And then we distribute the negative, and this will become a positive 3. Well, 8/3 minus 1/3 is 7/3, and negative 6 plus 3 is minus 3. If we look at this, let's just get a convenient common denominator. 7/3 minus 9/3. 7 minus 9 is negative 2/3. There we go. In the second one, letter B, we have a square root sign, so we're going to convert that to a rational exponent. Get that out of there. So this is the same thing as the definite integral from 1 to 4 of 3x to the half power dx. So we take the antiderivative and raise the exponent by 1. 3x to the 3/2 power divided by 3/2, or times its reciprocal 2/3. And that's going to be from 1 to 4. And let's see, 2/3 times 3 is 6/3, or 2x to the 3/2. And let me rewrite that. X to the 3/2, that's the square root of x to the third. And from our lower limit 1 to upper limit 4. So first we run the upper limit through. That's going to go in for x. So we're going to have 2 times the square root of 4 to the third is 64. Minus. Run the lower limit through. 2 times the square root of 1 to the third. And let's see, the square root of 64 is 8, so that's 2 times 8, or 16, minus 1 to the third is 1, the square root of 1 is 1, times 2 is 2. 16 minus 2 is 14. The last one, letter C, we're not having fun in calculus unless we do a trig function. So here we have the definite integral from 0 to 1/4 pi of secant squared dx. So now we got to think, what did we derive to get secant squared? Well, that's tangent. Tangent of x, and then we're checking that or evaluating that from 0 to 1/4 pi. Plug in the upper limit, the tan of 1/4 pi, minus the lower limit, tan of 0. Alright, what is the tan of 1/4 pi? You could do it on your calculator, but if you're on part of the AP test does not allow calculators, we have 1/4 pi is our angle. Our cosine value is root 2 over 2. Our sine value is root 2 over 2. Tan is sine divided by cosine, or 1. Minus the tangent of 0. Down here would be 0. This is 1, 0. And tangent is sine 0 divided by cosine 1, or 0. 1 minus 0 is, of course, 1. Here in example 2, we're going to look at an absolute value function. And if we remember, absolute value functions are in a V shape, and they usually do not go below the x-axis unless we have a plus or minus outside, or a minus outside of the absolute value bars. So what we're going to do here is first figure out where we hit the x-axis and then come up with 2 separate integrals. So if we were not provided the picture that goes with this function, we want to figure out where our absolute value equals 0, or what's inside of it, just 2x minus 1 equals 0. Add 1 to both sides, divide by 2. We know at x is 1/2, we switch from our negative sloped left half to our positive sloped right half. So this integral we're going to have to break into 2 pieces. First, we have the integral from 0 to 1/2 of this negative sloped line. And that's just what is in our absolute value bars with a negative. Negative 2x minus 1. And let's distribute the negative now. So it's going to be negative 2x plus 1. So negative 2x plus 1 is our first piece of the integral. That'll take us up to the halfway, or the 1/2 on the x-axis. And of course we got to add to that the other piece of the integral, and that goes from 1/2 to 2. From 1/2 to 2 of, now this is the positive sloped piece of that absolute value function. So it's just 2x minus 1. Oops, and I almost forgot my dx. Gotta have a dx in there. So let's take some antiderivatives. The first function here, when we take this, it's going to be negative 2x. We raise the power by 1 to 2, divide by the new power 2, and then we're going to have plus x. And that integral is run from 0 to 1/2. And then we're going to do plus our other integral. We take the antiderivative here. It's going to be 2x squared divided by 2 minus x. And that integral we will evaluate from 1/2 to 2. And of course these 2's will cancel, these 2's will cancel, but the negative is still there. We can't forget about that. And let's start running our upper and lower limits through. So first we're going to plug in this 1/2. 1/2 squared is 1/4, and it's negative 1/4. Plus 1/2. So that's our first piece. And then we're going to minus when we run the 0 through. So negative 0 squared is 0, plus 0. Negative 0 squared plus 0. That is our first piece of the integral. And then we got to add to it the second piece, and I'll switch over to red. So we plug in the upper limit 2, so we will get 2 squared is 4, minus x is 2. And then minus our lower limit run through. 1/2 squared is 1/4, and then we have minus 1/2. If there is a mistake to be made on doing an integration like this, it's in the grouping symbols. It's very easy to forget a parenthesis. It would be especially critical here, where we have to distribute that negative, which will turn this 1/2 into a positive. If you forget a grouping symbol or distribute a negative, it's going to mess up the whole problem. So let's get rid of our grouping symbols. Our first negative 1/4 is fine, plus 1/2. These zeros amount to nothing. And then we're going to have plus, and our next set of grouping symbols, the 4 minus 2 is okay. And then here we have negative 1/4, and then plus 1/2. So let's see if we can eliminate some of those fractions. Well, let's see here, negative 1/4, and negative 1/4 is negative 1/2. And that'll wipe out one of these positive halves. So those are now gone. And now we have 4 minus 2 is 2, plus 1/2 is 2.5. And let's write that as a mixed number, or I mean an improper fraction, 5/2. Of course, when you look at the graph, you know that we could have also got around this problem without calculus at all. We have two triangles. Area equals half base times height. We could do it separately for each triangle and find the same answer. But this is a good problem to demonstrate, to be careful with those absolute value functions, and to break our integrals up into two separate pieces. And here in example 3, we're going to use the fundamental theorem of calculus to find area. Remember, when our function is positive across the interval that we're integrating from a to b, in this case 0 to 2, the function is positive across that interval, so we can look at this definite integral as the area that's underneath that curve. So, find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2, the x-axis and the vertical lines x is 0, x is 2, as shown in the figure. So we have to set up our definite integral. Where we begin and end our integration is at 0 and 2. We can get it here from these vertical lines, or from the picture. From 0 to 2 we're integrating. Our function is 2x squared minus 3x plus 2 dx. Can't integrate without the dx. So let's perform the integration. Again, we're going to take the antiderivative of our function. That's going to be 2x to the third divided by the new power 3 minus 3x, and that's moved up to squared, divided by the new power, plus 2x. And our integration sign is replaced with a bracket on the right hand side from 0 to 2. So we start with the upper limit 2. We plug 2 in for x, and we'll have 2 times x to the third, or 2 to the third is 8 over 3, minus 3 times 2 squared is 4, divided by 2, plus 2 times 2 is 4. And then we subtract the lower limit run through the function. And this is going to be nice and easy because our lower limit is 0, and every term has an x. So we would have 0 minus 0 plus 0, which of course is going to be meaningless. That's just going to sort of drop right off. So here in the first set of brackets we have 2 times 8, that is 16 divided by 3. And then minus 3 times 4 is 12, 12 divided by 2 is 6, and a plus 4. Maybe this will be easier if we turn this to a mixed number. 16 thirds is 5 1/3. And then we have minus 6 plus 4, which comes to a minus 2. That subtraction leads us to 3 1/3. And then let's put it back into mixed number form, or I mean improper fraction. So 3 times 3 is 9, plus 1 is 10, 10 thirds.